we go. We just got done with normalizing, sometimes referred to as full annealing, right? Is that the last thing you got?
Yes.
Okay. Factors that affect recrystallization. So as they're annealing it, they're trying to get it to recrystallize, right? A minimum amount of deformation is necessary for recrystallization to occur. It's moving a little bit, right? You're heating it up, it's swelling up a little bit. It's relaxing the grains, making it nice and calm. The larger the grain size, the greater the amount of cold deformation required. To give an equal amount of recrystallization with the same temperature and time. Increasing the time of the anneal decreases the temperature necessary for recrystallization. So it's going to be in for a long time, you don't need to get it as hot, right? That's kind of like your tempering. 1.5 to 3 hours, right? Now we're going to look at the type of metal versus the temperature it needs. For recrystallization, so get to the left. Type metal versus recrystallization. Temps. That is short for temperatures. Oh, by the way, this is in degrees American. Does Donald Trump read a Celsius thermometer? I don't think so. The Don.
Read
aluminum. A silver medal with them. Just kidding. 175. Not very hot, right? Copyrighted music. How embarrassing. You gotta work on your ringtone. We need to get something a little more manly, I think.
I happen to like Sanford.
Sanford and Son. So we gave credit, so it's not copyrighted. I don't know if that works, but
Why are you trying to make money out of it?
I feel like you should. I feel like you should have something more along the Hanson.
Shut up!
A little umbop.
Yeah.
I think you should have an
Someone's
umbop.
got to set up there. My jerk off that kid from Bob.
Aluminum bronze. $660. It's a good round number. Beryllium copper. $900. Cartridge brass. $660. Think about the brass industry with the military. That's a big industry, right? Just for the military, not even the crazy gun people, right? It's a lot of. What if there's a. What the heck is that?
It's dead.
Is it dead?
Yep. Got one battery light.
You know what? I think the SD card was full. That's a failure. Anyways.
Did you hear the
Cartridge.
gun shop in Mayville?
Huh?
Did you hear about the gun shop going in Mayville?
Let's
Gun shop?
Gun shop going in Mayville.
No.
Yeah.
That's awesome.
That's for all the slicks.
Hopefully they sell ARs there.
Right across from the state building.
Copper. Oh wait, I had to put the number down. 250. Lead. $25 degrees. So it's recrystallizing in still temperature, right? Maybe that's why it's so soft. Mg, also known as magnesium. 150. Magnesium alloys. About 350. You all know what 350 is, right?
Tree fitting.
There it is.
Monster, tree fitting.
Tree fitting with a tree.
Tree fitting.
Monel. $100 Somebody said, what's Monel? We have a couple sheets of Monel out there that Barry brought in. And everybody was trying to weld it for stainless. And they said, well, is this gonna work for stainless? Now, I'll take a look at the composition. Nickel alloys primarily composed of nickel from 52 to 67% with copper, small amounts of iron, manganese, carbon, and silicon. Alloys with copper content 60% more are called copperon nickel. Copperon nickel? Copperon nickel? Art Deco is made out of Monel. Fun fact. So it is kind of like stainless, right? 'Cause stainless is comprised of a lot of nickel. Molybdenum and it's one of them stranger alloys. If you're working with it, you'll work with it a lot. If you don't work with it, you won't work with it at all, right? Nickel. $700 degrees. Low carbon. Steel. It's going to be a G. Tin. 25 degrees. And then zinc. 50 degrees. So those are the temperatures for just about, I don't know, every metal you'd ever work with. Kind of seems like the lower the melting temperature, the lower the recrystallization. Think about zinc, if you look on light poles or something that's out in the, where they put galvanization all over it, you can see the crystals, right? If you look at it, some of them are really big. Oh, that hurt. Right in the knee, below the calf. How steels harden. Mechanism by which steels are hardened is, here's a big fancy word for you, allotropic transformation quenching. We're going to go ahead and put ATQ for the future. So what does allotropic mean? Anybody know? Nobody's going to know.
Tropic thunder.
No? About to sneeze. Oh, that was COVID. Whew. Allotropy or allotropism, tropism, however you want to say it, is a Greek meaning other, is the property of some chemical elements to exist in two or more forms in the same physical state known as allotropes of the elements. So basically it means it can be in two different states. So that's why steel is allotropic, right? Because you can have it in face center or body center, right? It's pretty simple. It's just not a word you hear every day, right? So allotropic transformation quenching means that when you're quenching it, you're changing it to Martensite. It's a different form. hard form, I guess. Iron is allotropic.
Wow.
Gamma, which means most alloy steels change to face cubic centered crystal structures on heating above a certain temperature. So you're going from body centered to face centered. For steel, didn't we look that up? It was like 1600 to 2000 was the list. Most steels revert back to body-centered cubic when they go back below 1,333 degrees American. So you heat it up, goes to face centered, cools below 1,333 degrees, goes back to body centered. If the atmosphere was 1,600 degrees, steel wouldn't be magnetic, right? But the atmosphere is not 1,600 degrees, it's 70. Ambient temperature, right, 70 degrees-ish. I used to put that on procedures and somebody said, nobody knows what the ambient temperature is, you need to put 60 to 70. Okay. If there are no alloying elements present, then steel will always go back to BCC, aka body cubic centered. Long story short, bottom line, steel must be heated to austenite lost it, comma, and then rapidly cooled to harden. Huge point. If you get done with this class and you don't realize that in order to harden steel, you gotta heat it up and quench it, not bad. Scale of 1 to 10, it's like a 9. pretend is definitely gonna be the difference between non-ferrous and ferrous materials. Which are, ferrous is related to iron, non-ferrous is not related to iron, right? Materials. No, I wanna go all the way over. Go over, there we go. Quenching variables. I keep getting a lot of people asking me during tests, what is a variable? It's something that can cause something, right? It's part of the process. It makes the process happen or not happen or whatever. It's stuff that is occurring during the process. So a variable of me opening the door would be turning the handle or unlocking it or pushing the door open, right? It's making the process happen. So when we're talking about quenching variables, it's stuff that can happen, make quenching happen or not happen, right? One of the very big ones, if you're using a water, for the welders, what happens when you dunk a really hot thing in the water? It boils, right? Steams, but it also creates a vapor pocket around it. There's nothing even touching it for a minute. And by a minute, I mean a small amount of time. Not an actual minute, but vapor blanket. Occurs when the metal is so hot it vaporizes the liquid. So it creates a vapor pocket around that when you're putting it in there, causing it to slow the cool. When you do the blocks, they fill that into the weld, it's like 256 rods or something. That thing is freaking hot. Just the other day, somebody got burned in Olean, and they grabbed a hold of the block with their bare hand. You know. And you know what they did to try to cool it down? Stick it in the quench tank, which was full of boiling water for people dunking it, right? As that water gets heated up, if you're doing a lot of quenches, that you're heating the water, right? You're basically cooking it. So that's another factor to think of too. If you're actually trying to quench something to harden it, you don't want to use hot ass water, right? It's gonna make it cool, you know, slower. This causes an envelope. That goes back to the safety thing, right? This is what all companies are looking for. I didn't know I wasn't supposed to grab the ridiculously hot block with my bare hands. Nobody told me. Right, every company's going to kill safety and test you because they want to be able to say, oh yes you did, you said it right here in this test, right? Now is that on any test? Don't grab a hold of a ridiculously hot piece of metal that was just welded with your bare hand? No. You'd think so, but guess what, in the lawyer world, oh speaking of the lawyer world, we'll talk about that later. Everybody saw the plane crash?
Oh, yeah.
So, you know.
That, we'll talk about it later. This causes an envelope around the metal. Which insulates the metal from the cool liquid. Whoops, I'm not done yet. Causing cooling too slow. One way to combat this is to oscillate the metal, causing the vapor envelope to break. If you're ever out in the lab, you see welders quenching it, they shake it around, right? They're shaking it around trying to get it to stop boiling. When you quench something, you want to completely submerge it, right? If you go halfway in or go slow, it's going to boil on your hand, right? So when you take it, you want to dunk it down in that water, wait for a minute, and then pull it back out. A lot of people they try and put it in slow. I've watched it a number of times. And I'll stand in front of a class and say, don't go in slow, dunk it. And you'll watch them, they're going like this and it's steaming in their face. And steam is very dangerous. Last thing we got here, I believe, is quenching medias. Just a list of quenching medias. Quenching stuff you can quench it in layman's terms. Stuff you can quench it in. Quenching medias. First one is fake water. On my list it says tap water, so we're going to just say fake water. Tap water is loaded with stuff. Fused or liquid salts. Brine. What's brine, anybody know? Salt water, right?
Wouldn't that go with the last one?
Isn't that,
Don't you like?
isn't that what they put on the roads in Pennsylvania?
I don't know. I know something you can use for cooking. Use for ribs.
So Bets, what do they use on the roads in PA? No idea? You're PA, right? What do they use on the roads?
I think that is all. He's sand and shit.
Sand, a lot of sand, I
Sand
know.
and small crushed
Because they say
stone.
that Pennsylvania trucks last longer, right? Because they don't put the salt on like New York does, but I don't know. Soluble oil. So it's synthetic, right? Because oil and water don't mix, right? Tell that to Exxon. Mobil. Killing baby seals, right? Soluble oil is a synthetic material. You would probably know what it is by like our bandsaw. It's got that white fluid. That's a soluble oil. It's meant to mix with water. Synthetic lube. Synthetic liquid. I don't know what the difference is between synthetic liquid and soluble oil is. I always thought they were the same thing, but there's different consistencies of everything, so. Oil, we watched that knife get hardened in oil, right? oil hardening. Sometimes it'll be right in the name of the steel. It'll say oil hardening steel or air hardening steel. That's the next one, right? Air. Remember when I was telling you, people were doing weld tests and said, don't cool it down, just let it sit there. And I looked over there with somebody with an air compressor spraying air over it. That's a form of quenching. You're increasing the cool, right? Don't do that. Increasing the cool by air. That's not quenching, it's absolutely quenching. You're increasing the time, or increasing it, the time it takes, wait a minute here, decreasing the time that it gets cold. Speeding up the process, right? Furnace, that's if you're doing something, that's where you don't want it to get hardened, right? Slow it down. There's an engine block out there with a crack in it. And we're going to try and nickel weld it, right? We want it to slow cool. It would be better if we could put it in a furnace before you start, let everything warm up, fix it, and then slow cool it. It'll keep it from cracking, right? Cold box refrigeration. So put it in a fridge, right? Cold box refrigeration. What happened here? There we go. If you put it in the fridge, it's gonna cool it faster, right? It all depends on the material. It all depends on the application, what you're trying to do, right? On whether you want to go faster, slower, whatever. Quiz. Next class. With 3 exclamation points.